All right, let's talk about the future of flight. We've all seen the incredible images of eVTOLs, flying cars. But as someone who's spent a career designing these propulsion systems, I can tell you the real magic isn't just getting them off the ground. It's about proving they are so unbelievably safe, you'd put your own family in one. Today, we're going to pull back the curtain and look at the actual engineering that makes this happen. We're going deep on how you certify the future.
So this is the big vision, right? What we call regional air mobility. Just imagine, fleets of these quiet electric aircraft zipping between cities. That grueling 3-hour drive you do? Yeah, that could become a quiet 30-minute flight. This isn't some far-off dream. It's the next great leap in how we move, and believe me, it is right around the corner.
But, and this is a big but, there's a wall, and that wall is made of physics. The simple truth is that today's batteries just don't pack enough punch for the kind of city-to-city travel we're talking about, not when you factor in the massive safety reserves, the extra fuel, essentially, that aviation regulators demand. And they are absolutely right to demand it. This battery problem, this range anxiety, is the single biggest thing holding the entire industry back.
So when you're faced with a problem that big, you have to attack it from the top down. You have to rethink the architecture itself. And that's exactly what led us to this, the P13 hybrid system. From a pure systems engineering view, this is the key that unlocks that long-range mission.
So what is it? Well, the P13 is what we call a series parallel hybrid. And honestly, it's the best of both worlds. We've combined a super efficient thermal engine, think of it like a generator or a range extender, with a powerful battery and electric motor. Now, this isn't just about flying farther. The most important thing is that it creates multiple, totally independent power paths. And in the world of aviation, redundancy equals safety. It's that simple.
And here's where it gets really clever. The system is smart. It knows what it needs and when. So when you're taking off over a city, you're in pure electric mode, silent, zero emissions. But once you get to cruising altitude for that long-haul flight, it switches to parallel mode. That's when the thermal engine directly engages to drive the propellers with over 95% efficiency. And if your battery ever gets low, no problem. It can switch to series mode and use that engine as a generator to top off the batteries. It's a dynamic system that's always optimizing for safety and efficiency every second of the flight.
Okay, but here's the part that most people don't see. Building an engine that works on a test stand, that's the easy part. Building an engine that the world's toughest aviation authorities will sign off on to fly over cities, well, that is a whole other universe of difficulty. This is the real challenge. This is the certification gauntlet.
You see, if you want to fly globally, you need the blessing of the 3 big players in airworthiness. EASA in Europe, the FAA here in the US, and the CAAC in China. And here's the kicker. They don't all play by the same rules. They have different philosophies, different requirements, different definitions of what safe even means. So you can't just design for one of them. You have to build a system that meets the absolute strictest requirements of all 3, all at the same time. And this chart really lays it out. You've got Europe's EASA, which is very prescriptive. For their enhanced category, the rule is simple and brutal. No single failure can ever lead to a catastrophic event. Full stop. The FAA in the US, on the other hand, is more performance-based. They tell us, show us your new tech and prove to us that it's just as safe as what exists today. So our design has to be ironclad enough to satisfy EASA's black and white rules, while also being flexible enough to demonstrate that equivalent level of safety to the FAA. It's a tough balancing act.
So how do you solve that puzzle? Our answer is an approach we call the enveloped compliance architecture. It's basically a strategy to design to the highest possible standard from the very beginning. We used a MISI framework. That's making sure all our safety pillars are mutually exclusive and collectively exhaustive so they cover all the bases without stepping on each other's toes. We built the entire system on 4 pillars that bake safety right into its DNA.
Pillar 1 is that prime directive from EASA. No single failure. What does that mean? It means if a generator quits, an inverter fries, or even a whole battery pack goes offline, the aircraft keeps flying safely. Period. The P13's dual power sources, the thermal engine and the battery, are the direct physical answer to this rule. If one path has a problem, the other one is always there to get you home.
Pillar 2 is all about defending against the unexpected. It's called dissimilarity and segregation. For our critical flight computers, we use 2 totally different types of processors. Think of it like having 2 co-pilots who think in completely different ways. A single software bug is extremely unlikely to fool them both. Then we physically separate everything, the high voltage wiring, the cooling lines, so a single fire or a leak can't knock out both your primary and your backup systems. It's defense in depth.
Pillar 3 deals with a really cool physics problem you might not think about. It's called Paschen's Law. Basically, it says that air becomes a much worse electrical insulator the higher you go. So a high-voltage system that's perfectly safe on the ground could literally have electricity arc across components in the thin air at 25,000 feet. It's a huge risk. The only solution is to physically increase the space between all high-voltage conductors by 3 to 4 times what you'd need at sea level.
And finally, Pillar 4, fail-safe design. The decoupling clutch is the poster child for this. Let's say in an extremely rare event, the thermal engine completely seizes up. Well, that clutch is designed to automatically and physically break the connection to the propeller. It's engineered to fail in an open, safe state. This isolates the failure, protects the rest of the system, and allows the aircraft to continue flying to safety on pure electric power. It's designed to fail in a way that protects you.
So, it's great to have these 4 pillars on a PowerPoint slide, but that's not enough. Not even close. Now comes the hard part, proving every single one of those principles through an absolute ordeal of simulation, analysis, and yes, destructive testing.
To do that, we live and breathe by what's called the aerospace V model. It's a simple but powerful concept. Every single requirement we write down, from a tiny line of software code all the way up to the performance of the entire system, is meticulously traced to a specific verification test. There are no assumptions. You design it, you build it, and then you prove it.
And I mean, we prove it. We have a ground test rig we call the Iron Bird. It's a full-scale replica of the entire propulsion system. On that rig, we will run 10,000 complete mission cycles, takeoff, cruise, land, switching between modes over and over again. We do this to find any potential mechanical fatigue or software glitches under the most punishing, long-term conditions you can imagine.
And then, you have the ultimate trial by fire. I mean that literally. This test is required by a standard called DO311A. We take a complete, fully charged battery pack, and we intentionally trigger a thermal runaway in one single cell. We force it to catch fire. The test is brutal and simple. The system must prove that it can contain all that fire, all that heat, all those toxic gases for a full 15 minutes without it spreading to any other cells. It is a one-shot pass-fail test, and there is zero room for error.
So, after all of that, all the design, all the analysis, all the testing, all the fire, it all boils down to just 5 final non-negotiable criteria. If the system can meet these 5 benchmarks, it earns its type certificate. That's its official license to fly. Think of these as the 5 final questions on the exam. 1. Can it survive any single point of failure? Yes or no? 2. Can that clutch transition from one mode to another, mid-flight, absolutely seamlessly? 3. Did we prove with a real test that thermal containment works? 4. Is it electrically safe at 25,000 feet? And 5. Is the software, the brain of the whole thing, proven to be reliable to the absolute highest standard in aviation, something called DAL-A? You have to get a perfect score. You have to answer yes to all 5. This quote, it's actually from our own internal engineering specification, and it's really the philosophy that guides everything we do. It's not enough to have a clever idea. Every single choice, every component, every line of code has to be backed up by a mountain of hard evidence that proves to the regulators and to ourselves that it is safe.
So you see, with this incredible level of rigor, the question really isn't if we can build these amazing flying machines anymore. The technology is here. The real question we're left with is about us. It's about trust. After all this work, how soon will we, as a society, be ready to step inside and trust them to carry us to our future?